was representation learning. Right, so can you learn more compact representations of high dimensional vectors, right? And to that end, one formulation that we started looking was the best fit subspace problem. Okay, and this led us to the definition of the first principal component. Okay, and what we'll do today is to talk about how you can reduce the best fit subspace problem essentially to the best fit line problem. Okay, so you can think of it as a reduction, reduce subspace to line. Right, if you can solve the k equals 1 case, then you'll be able to solve the higher k case. That's what we are going to show. Okay. And then we'll look at a different problem called low rank approximation. It's kind of, one way to think about it is this sort of a dual to the best fit subspace problem. And then we'll see some applications of it and then connect the two together with an algorithm for solving both problems. Okay. All right. And new announcement. Assignment 2 will be out today. Okay, today at 10 p.m. And as usual, will be due on next Monday at 10 p.m. Okay, you'll use Gradescope again. And assignment 1 should be graded today or tomorrow. Will likely be graded very soon, so it should be out soon. Okay. All right. Okay, so just a quick recap of what we were, talking about last lecture. So remember, we had, if you had a collection of points, then, and you're trying to use a subspace to approximate them, we had this notion of error. Right, and then we also had this notion of variance, which was to maximize the length of these projections. Okay, so minimizing the error was the same as maximizing the variance. And then we defined the first principal vector as kind of the solution to this problem when the subspace had dimension 1, right? So the first principal vector was a solution to the max for all vectors of the length of x times v divided by the length of the vector v. Okay. All right. So we showed that span of first PC minimizes right. So that will be the line which minimizes the error when you restrict to dimension 1. Okay, now what do you do when you have higher dimension, right? And towards the end of the lecture, several of you suggested some, made some suggestions. One was to use a greedy way where you start with finding the first principal vector, and then somehow you want to take it out from consideration from your data set, and then again find the first principal vector. Okay, you want to do some iterative way to compute one vector after the other. Okay. So there are various ways to do it. All of them kind of work, but I'll use one which is more conducive to the other interpretations we're going to look at. Okay. So this is the greedy approach, for solving best fit subspace when dimension is 2. Okay, again, we have to make sure it makes sense, but heuristically, at least, I think it's a reasonable thing to try. You first find the first principal vector. We'll talk about how to find it later, but let's say you can actually find it. So you found the first principal vector, principal component, then what do you do? Any suggestions? So, if you think about it, like let's say you had a 3-dimensional data set. Right, so you have a bunch of points, all over the space. And in some sense, you found a line maybe you just found a line that kind of approximated the data set the best you can if you were only allowed to use a line. Okay, but now you're looking to find a subspace of dimension 2. So you want to find like a plane. So what would you like to do? It makes sense to look for a plane which contains this line in the first place. But that was the best fit line. So we made a good start. So why throw it away? I would like to find something which kind of extends what we already found. Can I find something like this? Right, that makes sense, right? Maybe let me draw a picture better so that it's more illustrative. Okay, so I want to find a subspace of dimension 2. And I already have one direction of the subspace. Kind of that's the idea. We already found one principal vector, so we need to find the other principal vector or something which describes the subspace in a concrete way, but contains this line, right? So what can I look for then? Well, think about what we said about finding a subspace. What would it mean to find a subspace of dimension 2? You needed to find a basis for it or an orthonormal basis for it, right? And we are saying, okay, we'll start with this v1 as one of the vectors. So the other vector should be perpendicular to it. Okay, again, it's kind of a natural thing to try. Okay, so our greedy approach, one greedy approach is to find direction that once again maximizes the variance of your data set along the direction v. Okay, remember v1 was the direction which maximized the variance along a direction. I'm going to ask for the same thing, but this time I don't want to end up with something which is v1 again, right? So that's the first solution, we all agree, but now I want to find the second best solution, right? So how do I exclude that solution? I can say that maximizes find direction v, that maximizes this while being perpendicular to v1. Yeah.
So we can enforce that either as a constraint, or we can add this as like a regularization, right? Since as long as it's not within the span, we can always just take it from.
Right. But when you're looking to quantify it as the variance along the direction v, it has to be perpendicular. Because, if I don't put perpendicularity, maybe you'll find something which is 90% correlated with V1 and will still maximize this and is spanning two things still.
You can't just take the
It might not be the best one. Right, so when you say maximize, I definitely don't want something which is V1.
Yeah.
Right. So how do you enforce that? That's the main constraint. Right. And the way we are saying is, okay, if you don't want anything related to V1, let's just ask for it to be perpendicular to V1. Okay. And if you dial that knob a little bit, you won't get the same answer. Okay. So we want to say find something which is perpendicular to V1. And I mean, there are many vectors which are perpendicular to V1. Remember, even something which is outside this will be perpendicular to V1, right? But find something which is perpendicular to the first principal component and maximizes this. Okay. This is one greedy approach. There's an alternate greedy approach. As it happens, both of these are equivalent. It requires a little bit of linear algebra to prove it, but let me write it down as well. Okay. The other greedy approach is to say, now imagine you're trying to approximate some, quantity or some vector, right? I find a first order, first something which approximates it. To improve my approximation, what should I approximate next? Imagine I make a device which gives me a first rudimentary measurement. Now, to improve my measurements for better accuracy, what should I do next? I need to somehow measure the gap, the error. Right? So I'll first start with an approximation and then try to approximate the error which is left over. Okay, so you're basically trying to iteratively keep improving your quality of approximation, right? And okay, so here, we have a bunch of points once again. Okay, let's say this is my V1. Okay. Now, what I can do is, as I said, one way to think of this line is you project every point onto the line. Okay, and so on. Right, so we have this projection vectors. Okay, so we are simplifying all of the points as a first guess to points on the single red line. That's our principal component. Okay, so now if I want to improve my approximation, it makes sense to just try and approximate these error vectors. Okay, so what does that mean? Idea 2 would still be find the first principal component, V1. And then you form a new data set. Let's say xi bar, which is xi minus the projection onto V1 of xi. Okay, so these are essentially the error left over. Right, so form a new data set which contains only these sort of perpendicular, these error vectors. Now try and approximate it again the best you can with a single direction. Okay. So here you'll say, maybe find the first principal component of the new data set, x1 bar, x2 bar up to x. Okay, you can call this your V2. Okay. Again, this is a common method where you're trying to approximate something, you get a first guess, and then you try to approximate the error and then keep on improving it as you go along. Okay, so that's what we are doing here. And as it turns out, and as you'll show in your homework, these two give the same answer. Okay, both of these are actually equivalent. They look like two different things, but mathematically, they are the same. Okay. Depending on your view, one could be more natural than the other, but both are anyway the same. Right? And just for algebra, the first formulation is actually nicer when you're trying to compute things. So we'll try and use that. So it's a little bit more compact. Okay, so let me now define the second principal vector, or the second right principal component, or second right singular vector. This is also called that. Yeah, as we'll see. And this would be any vector which maximizes the length of x times v relative to its own length, just as we did for the first principal component. Okay, but we're going to insist that the vector v be perpendicular to v1. Okay, so this is the part which says that v is perpendicular to first principal. Okay. Any questions? All right. And once you have the first and the second, you can imagine defining the third and fourth. So how would I define the third? Let's say I have defined v1 and v2. For the third, I will say, okay, find me the vector v3, which would maximize this ratio. But now I want it to be perpendicular to both the first and the second. Right? And if you go back to this sort of second view, you're basically say that, okay, I found one direction in the second direction. I'll take off these things, and whatever is the error left over, I would try and approximate that. Okay, so all of these are the same. Okay. So if I've already defined v1, v2 up to vi minus 1 are the first, second, third, up to I minus 1 right principal, right singular vectors are principal components of the data set. Then you can define the next one as the vector that maximizes this ratio, right? Subject to, actually, we were doing, let's put the normalization right here. Okay, so I want it to be a unit vector But more importantly, I want it to be perpendicular to all of the other principal components that you have found. Okay, this is at this point, it's still a definition, right? We're just defining things, and we'll later talk about how to find them. Okay, so okay. And remarkably, and we got lucky, I would say. So it's a hard non-continuous optimization problem. And if you even if you make small tweaks, but in the end, the way we define error and everything, it turns out that the span of the first k right singular vectors maximizes okay. So this greedy approach of finding one after the other does in fact solve the full optimization problem. Okay. I mean, greedy approaches are usually kind of heuristically pretty reasonable, but many times they don't give you the right answer. But for this specific problem of finding the best fit subspace, it does actually work. Okay. It maximizes this, or equivalently minimizes okay. All right. So one thing I want to say, I mean, this I also briefly mentioned earlier, but let me reiterate it. Oh. Now, if we had defined so if we define the quality of a subspace as sum of the error lengths without the square. Okay, so we chose a square, no particular reason was given except that, I said that's the best choice. But if we had done this, which is again qualitatively achieves the same function, right? You're looking at how well your subspace averages, approximates the points on average. Okay. Why sum of squares and not sum? Well, there's a very important computational reason. If you define it this way, then the greedy algorithm fails. Right, so you cannot find the first principal component and then try and do something after that, and so on. So it won't work. Okay, even if you had the ability to solve the best fit line under this specific quantification of what it means to be a very good fit, you wouldn't be able to use it repeatedly to solve the higher dimensional problem. Okay, so there's something special about putting a square here. Okay, any questions about this? It's not something we're going to explore, but just I want to say why square is important. Yeah.
So when you're talking about like the
So yeah, so the square is not really part of the method, right? The method is saying, you take it out and then use whatever you're doing for k equals 1 on what's left, right? If you do that, even then you won't be able to solve the best fit, k equals 2 problem this way. If there is no square, you cannot solve it one step at a time. You have to somehow solve it by finding both the directions together. Okay, the fact that you can find the best fit line and then something is special about the the objective that we chose, which had a square. Yeah. It's a good question. I mean, one vague intuition is that when you when you put the square, perpendicularity really helps you, right? If your things are perpendicular, everything, you have exact equalities all the way, right? But when you don't have the square, you do not get equalities in sums of lengths unless they're perfectly aligned, right? That's one sort of, mathematical reason that shows up. Okay. Essentially because of Pythagoras' theorem, right? If you're in 2 dimensions, if you do orthogonal projection, the length is sum of squares of the length. So you're trying to mimic or kind of go backwards from that form. Yeah. Sum of the 2 norms, but without the square. It's sum of the 2 norms and not sum of the norm squares. Yeah. Okay. Okay. All right. So, I'll prove the special case of this theorem, which is for k equals 2, that has all of the ideas, and then you'll extend it to the general case in the homework. Okay, so the span of the first 2 principal components solves the best fit subspace problem for k equals 2. Okay, so that's what we want to show. So what does it mean more precisely? So you have the first principles, first principal component. Okay. And then you also have the second principal component. Okay. So let's say, let S be the span of V1, V2. Our claim is that, this, maybe let me use SPC. The span of these 2 first principal components gives you the optimal solution among all 2-dimensional subspaces. So you want to say that among all 2-dimensional subspaces, this would maximize the variance. Okay, so that's what we want to do. So let's try and first do some sort of groundwork to use it. Okay, so this is my, let's say V1. And remember, by definition, the second principal component must be perpendicular to V, right? So you only look for the vector which maximizes the inner product, the length of the inner product, x times V, among things which are perpendicular to V1. So it has to be perpendicular. Now let's say I have another point X here. What was so what is variance of X to SPC? Okay, so to compute this, I need to project this point X onto this plane and then look at maybe right. So this is going to be summation I equals 1 to n, the length of the projection of xi onto this. Okay. And here we're going to use another fact from linear algebra. Okay. So what's the linear algebra fact? So my claim is that you can compute the length of this blue line square easily by computing inner product. Okay. So why is that and how do you do that? So more specifically, suppose I have two orthonormal vectors W1, W2. Okay, so I have two vectors which are perpendicular and of unit length. Okay, these are two perpendicular vectors. And if another point X right, so let's say T be the span of these two things, W1 and W2. Okay. And this is the projection of X onto the point T. The claim is that the length of the projection of X onto T squared is exactly this much. Okay. Why is this true? Essentially because W1 and W2 are perpendicular, right? So I can compute the length of the square by projecting this line further along the directions of W1 and W2. Okay. Okay, but let's take this for granted for now. Any questions about the statement though? It's just saying that I can easily compute the length of the projection onto a span of orthonormal vectors by looking at sum of squares of the inner. Okay. And the proof would be like, I can use Pythagoras' theorem to say something like this. All right. Okay. So let's use this for this part. So what do we have? So we want to compute the variance of S of X in the subspace spanned by the first principal components. So that would mean I need to compute the lengths of all of these projections. The first two principal components are perpendicular, so I can use this formula to say this is exactly okay. So which I can break up as okay, and this would be x times v1 squared plus x times v2 squared. Okay, so this is the length of x along, the length of x times v1 squared times length of x times v2 squared. It's just more compact notation for the same expression. Okay. All right. So what do we want to say? We want to say that SPC is the optimal value, is the highest value that you can get. So how can we show that? So pick any other subspace T. So let's say any other two-dimensional subspace. We want to say that SPC is the best maximizer among all two-dimensional subspaces. You pick something else and let's compare the two. You want to say the one is better than the other, but let's see how we can do that. And let's say T is a span of two vectors W1 and W2, which are an orthonormal basis. For T. Okay. So what does this mean? What do we get? So we want to compare the variance of x along T versus variance of x along SPC. We just saw that I can write this as x times v1 squared plus x times v2 squared. How can I write this in terms of these two vectors? In terms of the orthonormal basis? The same thing, right? I can still say that, variance of x comma t, summation, look at all of the points, the projections of xi onto t squared, which we know is just right? So which is once again okay. So we get two terms here again. So this is also going to be all right. So we have to compare the blue box number to the green box number. Okay, how can I compare these two? There are two ingredients. Can you at least say something about one-on-one comparison or no? So ideally, we would like to say that the right-hand side is bigger than the left-hand side. Okay. What's the least thing we can say? Was the first, we should be able to say something. I claim that you can say something already from the definition of the first principal component. What is that? Well, remember what was the definition of the first principal component? So recall V1, the first PC, maximized Yeah.
But we know that x dot v1 is bigger than all of definitely for anything other than v1. So we know it's bigger than either x dot w1 or x dot w2.
Right.
So we
Exactly.
Replace something on the left with quality, and then we can use that for
Right. So that's exactly the start I was looking for. So by definition, the first principal component maximized this. That was a vector which maximized this among all unit vectors, right? So at the very least, this term x dot v1 would be higher than either of them. Okay. So maybe let me move this here. So by definition of first principal component, this must be true, and the same for the other one. So we are trying to compare the sum of two things, and we at least know that one of this, quantities on the right is bigger than the other two. But how about the next one? How can we compare this to either? Can we directly compare? Can we say that x dot v2 should be, okay, let's say I pick x dot v1 is bigger than this. How can I argue that x dot v2 is bigger than this? That would be the natural thing to do, right? But can I do such a thing? What do you think? Well, it turns out that it's not that simple. Okay. Yeah.
v1.
Oh, sorry, this should be v1. Thanks. Otherwise, you would be done. Yeah. So we don't know about v2, right? So we don't know how to compare v2 to this. Okay, but what can save us? Okay. In fact, if you pick a arbitrary basis, it won't be true. There will be bases where x dot v2 will be smaller than both of them. Okay, but what could save you is that the first quantity is pulling more than its share, so that's so much bigger that that kind of dominates the sum anyway. That can easily happen. Okay, so how do you get around this issue of not being able to compare v2? So what do we know about v2 though? Again, recall the definition. So we know v2 maximizes x dot v squared among all vectors which are perpendicular to v1. Right? So v2 maximizes this length, but only when you constrain to look at things which are perpendicular to v. But a priori, there's nothing to say that w1 or w2 should be perpendicular to v. Right? If one of them were, we would be in good shape. Okay, but we don't know, that need not be true. I can pick many, many different bases, and one of those bases need not have this problem. Okay. So the way we get around this is, again, to use linear algebra, which is for any subspace, there are many, many different orthonormal bases. Yeah?
Suppose w1.
So we are going to do something like that, but you have to change both vectors. You cannot change just one. If you only try to change just one, it won't work.
Oh, you just changed that.
No, change the w1 and w2 together. Yeah. Yeah. Yeah, exactly. So the point we are going to use is that in this statement, this is true for any orthonormal basis, right? And for a subspace, there are many, many different orthonormal bases, right? If these two form an orthonormal basis, actually, let me draw a better picture. Maybe something like this. Okay, so let's say this is T. Okay. Now, this is one orthonormal basis. Okay. But there are many, many different orthonormal. I can rotate this by a little bit. The first vector by a little bit and the second vector by the same amount. And I would get another orthonormal basis. Right? I can keep rotating them, and every one of those configurations is an orthonormal basis. And for every one of them, I can use the same formula with calling this one W1 and calling that one W2. Okay. So the clever ingredient that we're going to use is the following. So let's say this is our, again, I'm going to draw it in an exaggerated way. Kind of distorts the lens a little bit, but it's helpful for visualization. Let's say this is my vector v1. Okay, I'm saying I'm drawing it in an exaggerated way because v1 is also a unit vector, so it has to be small. But I want it to kind of go out to make sure that it's like a 3D vector. Okay. So my claim is that there exists an orthonormal basis for T where W2 is perpendicular to V. For any two-dimensional subspace T, I can find a basis where the second vector is perpendicular to my vector v1. v1 is arbitrary, it can be anything. It could be highly correlated with the subspace T. It could be not in the subspace. It doesn't matter. My claim is no matter what vector v1 you pick, I can find a basis where W2 is perpendicular to v1. Okay, and how can I do that? Initiations. Again, you can give like a visual answer if you want. That's totally fine. Exactly, right? So as I said, just imagine you have this 90-degree angle and then you're spinning it around. Right? I'm going to spin it around until one of them is perpendicular to my purple line. Okay, it has to happen some point. Like if it's going to come around fully. So at some point it is going to actually be perpendicular. That's when I'll choose my basis. Okay. So technically, you would say, okay, just project v1 here. And maybe let me erase this guy just so it's not too confusing. Again, it's not to scale, so say this is what I do. Call this W1, and then I pick the one which is perpendicular to it. This is W2. Okay, does it make sense? Saying that for any subspace, I can pick a basis where one of the vectors is perpendicular to my vector of choice. Okay. So what does this buy us? So what do we have now? So we have, T is span of W1 comma W2. And we know that W2 comma V1 is 0. Okay. So we can redo the calculations. By the same calculations, okay, this is true. And by the definition of the first principal component, we must have this. Okay, the first term should be at most x times v1 squared, just by the definition of the first principal component. And further, by the same logic, we should also have that the second term is at most this, because of the definition of second principal. Okay, now W2 is perpendicular to V1. Among all such vectors, V2 maximizes the inner product. So this must be at least this much. So now we have, both terms are both larger than the corresponding term. So the sum is also larger. Okay. So the span of the first two principal components does indeed solve the two-dimensional best fit subspace problem. It is a subspan which maximizes the inner. Okay. So implies yeah.
So why does it matter, W2 and V1?
Because remember, in the definition of V2, it only maximizes this inner product in this space. It's the largest one only when you're constrained to look at things which are perpendicular to V1. Right? It's only because of that. So since we have that W2 is perpendicular to V1, we get this comparison. Right? So x dot W2 is less than or equal to x dot V2 because both of them are perpendicular to V1. And all vectors which are perpendicular to V1, we know that V2 is the one that maximizes inner product. Okay. If we didn't have this, we wouldn't be able to make this comparison. Okay. Any other questions? Okay. So, I mean, you can extend the same argument to higher k and reason that the span of the first k principal components actually solves it for all of the things. And it can be done by simple induction, more or less. Okay. All right. So let me stop with that for best fit subspace problem. But basically, what did we do so far? What we did was to somehow, maybe let me say that more explicitly. So summary. We define the problem of best fit subspace, right? And then we said finding the first k principal components of X will solve the best fit subspace problem. Okay. It is helpful, but we still haven't really solved the problem because It almost looks like we reduced it to finding the principal component, but we have to now discuss how to find the principal component. Okay. All right. So let's take a short break. And when we come back, what we'll do is to talk about a different problem and see how we can use that, how we can solve that also using principal components, and then how to solve both of them together. Okay. All right. So let's take a short 5-minute. Okay, so the next problem that we're going to talk about is what's called low rank approximation. Okay, so let me define it formally, and then we'll talk about some applications of it and some history behind it. Okay, so here so you're given some big matrix, or assume that you have some access to this matrix, which is an n by d matrix. And let's call it X. And this is too big a matrix, so you want to approximate it. Okay, I want to approximate the matrix X by a simpler matrix. Okay, so that's the high level goal we're targeting. We have this big matrix n by d, and I want to approximate it by a simpler matrix. So to make this quantitative, we have to define these two terms. Now, what does approximate mean? What does simpler mean? Okay, so as kind of indicated in the title of low rank approximation, what does simple mean? There are various notions to think about, but the one that is most meaningful in many fields is to use simple is like low rank. Okay, it's a very old method, kind of keeps resurfacing every few years as a new tool that people discover. Most recently, people are using this again for kind of fine-tuning large language models. Okay, I'll say a few words about that towards the end. Okay, but the basic thing is that I want to approximate a big matrix with something simpler, and simple here is going to be something which has low rank. Okay, and remember the definition of the rank of a matrix. Rank of a matrix is the span of the rows of X, which is also the span of the columns of X. Right? But for us, the most the best way to think about simplicity is that a matrix X is of rank R only if, I have this big matrix X, which is n by d. It is of rank R only if I can factor it. I can write it as a product of two much smaller matrices. Okay, let me exaggerate it again. Okay, so I'm writing X as a product A times B. X is n by D, A is n by R, and B is R by D. So okay, so where matrices of rank R, if and only if I can write it in this way. Okay, so it kind of makes sense, but why? So let's tug on this thought for a little bit. So why study rank as a notion of simplicity? Yeah. That's definitely a very good point. So for instance, especially for storage, it's massive savings, right? So to store X, we would need n times d parameters. Okay. Whereas to store, A comma B, we would need n plus, you need to store A, which is n times R, and you need to store B, which is R times D, which is n plus D times R. Okay. So for example, if n is 10,000, R is, again, these these are still pretty small numbers. So D is 10,000, R is 2. It's a huge saving. And if you can do it, that would be huge saving. Okay. So sometimes you might be willing to, take the cost of approximation at getting this significant savings, both in terms of representation, just in terms of storing the matrix. That's actually one of the main places where it shows up in the recent works on low rank adaptation because of memory constraints. It can reduce the memory footprint significantly. Okay. And the next thing we need to do is to quantify approximation. Oh, actually, let me also say that along with this computational reason for memory, right, even multiplying matrices is easier with low rank factorizations. Right, just as storing is easier, even multiplying would be easier, right? For example, let's say I want to calculate X times a vector V. How much time would I need? Well, X is n by D, and my V is d-dimensional. So I have to compute n entries. Each computation involves d multiplications, d addition. Right? Each time I have to multiply a row here with a column here and so on. Right? So it takes O of n times d time. Okay. Whereas if I have X is, A times B, this is n by R, and this is R by D, and I ask you to multiply X times V, what would you do? Would you first multiply A and B and then multiply with V? Well, I can either think of it as this way, or the better way is to do it A times B times C. Okay, because these are, kind of smaller vectors and matrices, right? So, computing B times V will take R times D time. And, computing this will take an additional N times D time. So the total would be N plus, sorry, this would be N times R. Okay. So even matrix vector multiplications would be much faster if you have a low rank. And the final reason, which is something again we're not going to discuss, is that there are good statistical reasons. In some cases, you can build good statistical models which kind of naturally lead to matrices which should be close to being low rank. Okay, so in all of these senses, low rank is a pretty good assumption to make. All right, and the final thing before we formulate our algorithmic task would be to quantify approximation. Right, so we zeroed in on a notion for what simplicity means, but what does approximation mean? Okay, so we have this matrix X. We want to approximate it with this lower rank matrix. The final dimensions of both matrices are the same, but the other one comes with a better representation or more compact, compressed representation. Okay, so what's the approximation that you should take? There are various notions. The most versatile is what's called the squared error. Or RMSE. Okay. So here you just look at each entry, compare the squared error between those entries. Right. So I can do this. For each entry xj, how far is my gap to in the ij tilde, and then sum of squares. Squared error would be this. And usually in data mining, this is actually called the root mean squared error. That's what you would see more often. Do the same thing with the square root for the entire. Okay. All right. And let me introduce some notation. Again, this is classical notation. For any matrix A, you can define what is called the Frobenius norm of the matrix. This is denoted AF. F is Frobenius, which is just sum of squares of the entries of the matrix with the square root. It's a little bit like the Euclidean norm, sum of squares of the length of a vector, but here you're taking the entire matrix as a vector. Okay. So in that sense, the RMSE is just look at the error matrix, which is x minus x tilde, and compute its Frobenius norm. right? So when you take the Frobenius norm, you have to take the sum of squares of the entries and then put a square root. Okay, so we are now ready to define our low rank approximation problem. So the input to the problem would be some matrix X and a parameter K, which is kind of the rank bound that you're looking for. And I want maybe the best rank 1 approximation, best rank 2 approximation, and so on. And the output should be a matrix X tilde to minimize of rank at most K to minimize the error. Okay. So among all matrices of rank at most K, find me the matrix which gets the least Frobenius error from my input matrix. So that's the low rank approximation problem. Okay. All right. So there are various applications of the problem, but let me describe perhaps the most popular one. And this relates to what's called the Netflix challenge. Okay, this was something that kind of just came about when I was starting my grad school many, many years ago. Okay, so what is the Netflix challenge, right? So back in the day, I think this was, this is actually well before the streaming stuff started even. It was the DVD days. And so the situation was that, okay, you had, if you think of Netflix, you have users, right? And then you have movies. Okay. Imagine I start filling out this users movie matrix. And for each movie, I write down, okay, these are okay, so you have these things, and each user rates some movies. Maybe some movies are rated 4, some are 0. Maybe this is a 5. And star indicates that that user did not rate that movie. Okay, and what was the challenge? It was almost like an ML competition where they said, okay, we're going to give you this much time. There's a leaderboard and so on. But they released this matrix with 500,000 users. Okay, and then 17K movies. So it's a huge matrix. At least back in the day, I couldn't even fit it on my RAM. And you have 100 million entries. Okay, so you see 100 million entries, and to kind of get a sense of this number, that's basically like 1% of all possible entries are seen. Okay, so you have this huge matrix, but you don't know what all of the entries are. Not every user goes and rates every movie. You know, some of them still did pretty good. You know, they're rating so many entries. 100 million entries are rated. Okay, so that's roughly 1% of all possible entries. So on average, each user has rated about 170 movies. Okay. And what was the goal? The goal is to guess the missing scores. Okay, so say, okay, we're going to release, you know, what some part of the matrix that we know, and we want you to build a predictor which will guess the remaining entries. Why would a company like Netflix care about it? Guess their suggestions. Yeah. For recommendations, right? In fact, another name for this whole thing is collaborative filtering, meaning you're using this data to suggest recommendations. In particular, if I can guess the stars, then I can, you know, say, okay, maybe you should go check out these other movies that you might like. Okay. And how are they actually evaluating it? So you propose a model, and they would score you based on the average root mean squared error on some holdout entries. Okay, so even Netflix did not have the full matrix with them, but they did not show all of the entries that they could. Right? They maybe had 2% of the entries, they only showed 1%. And based on the model that you predict, they're going to look at the other holdout entries that they kept from you and see how well you're doing there and take that as kind of a guess for how good your model is. Okay. So, you roughly need about 8 GB to store the matrix. Okay, 8 GB RAM to store the matrix. Okay, so what was the challenge? Okay, so the challenge they said was, okay, we have a baseline method which gets this much accuracy. They use whatever, they had their own internal thing. And they said the first team to do better than 10%. Okay. They said, we have our baseline model, it gets this particular score. And if you beat our performance by 10%, they're not saying solve the problem fully, but if our score was like 0.9, then your error score should be like 0.81. If you beat 0.81, which is like 10% better than what your model is, then you're going to get $1 million. That was their claim. Okay, kind of a very good PR. It generated a lot of excitement. A lot of people worked on it, and it became a pretty good pastime for for ML researchers as well. Okay, it's a very well motivated problem. Kind of shows up in many different places. And one of the best things was that for the first time, at least at that time, maybe almost a decade or so ago, first time we had access to such a big data set for this specific problem publicly. Yes, it was a very good place to try out algorithms. Okay. So let's see what we can do in the context of low rank approximation and what happens there. So the first step, if you're asked to solve this problem, the first step would be, to do some data cleanup, right? So let's do that. Let's pre-process the data to center this course. Okay, meaning some people are just, like any movie, they would probably never go below 3, like 3, 4, 5, 3, 4, 5, 3, 4, 5. Whereas some people probably hit all movies, they'll just be 0, 1, 0, 1, 0, 1 or something, right? You want to kind of, normalize this course a little bit. So let's say at the very least, center this course so that they have mean 0. Okay. And the next thing I'm going to do is once I have mean 0 for the known entries, this is only on the known entries. We don't see the entire matrix. So we have all of these stars. So what would be a good value to put for the stars after I do the centering? 0, right? It kind of, it's basically like saying if I don't know what star is, my first guess would be the average rating. And I'm going to look at how you like movies, and then I'm just going to say, okay, the average score is what I'm going to start with. Okay. So step 2. Put 0 for every missing entry. Okay, so now you have a matrix which is fully numerical, right? There are no stars. You have numbers everywhere. Okay. And step 3, imagine you can actually solve the low rank approximation problem. Okay, if you can actually solve the low rank approximation problem, can you use it for this problem now? Any guesses? Yeah. So, okay, so the idea would be to find, I don't know why it's not. Find the best low rank approximation to X. Let's call it X tilde. Okay. So even though you put in zeros for the missing entries, in X tilde, the entries need not be zeros, right? Because you're putting this low rank constraint, which is some kind of regularization. So pretty strong constraint to put. Okay. So for the next step, you do predict according to X tilde. Predict all of the missing entries according to X tilde. So you put in zeros or fill in the missing entries with the average values, and then perhaps refine it by finding the best low rank approximation to the matrix. And then use the new entries to make the prediction. Okay. So why should this be a reasonable thing to do? Any guesses as to why? The heuristic reasoning that people had was that, maybe there are some low rank factors which make this matrix approximately low rank. Right? You can imagine that I can estimate the score based on there being some weight I give to specific genres. Right? Maybe I like action movies more. Maybe I like action. I give some, action movies I like 0.9. Comedy is 0.8. Romantic movies I hate, so 0.1. right? Things like that. Based on this sort of categorization, maybe I can compute an overall score. If you had such a statistical model, it will naturally lead to score matrix being approximately low rank. Okay, so there are some good statistical grounds to think it could be close to a low rank matrix. So you're trying to find out the best low rank matrix approximation. Yeah. It doesn't even have to be that. It could be, that's definitely a bit more constrained. Yeah. Right? We're not putting any non-negativity. We're just saying lowest rank approximation. Okay. Right. So what happens if you do this? Hold on. So what people found was that this sort of simple method okay. I give up. I know what's happening with this today. I wonder if it's a charging. Yeah. If I unplug it, it works better. Okay. So anyway, so people found out that if you just run this experiment, if you run this with k equals 30, and you need to understand that low rank approximation was a problem that was basically solved in the 1930s. Okay, it's been known, it was a standard staple in data mining, data science, and everywhere, like almost 70 years before this. And if you just did that with rank 30, remember this is a pretty big matrix, it has 17,000 columns, but I'm only trying to approximate it with 30, rank 30. Okay. So what happens then? You beat Netflix baseline by 4%. And remember, they said, okay, 10% is $1 million. They didn't scale it down. There was a threshold. But even doing this very simple, like, first technique that anyone would try if you had taken any course, would have already given 4% boost. Because I don't know what they were doing because they didn't do it. They probably never took a course like ours. Okay. All right. And I should say that this problem, this is called matrix completion now. And it has a lot of literature on it. I have some work on it too. And we'll talk about some other things about this problem a little later. Okay. So matrix completion is the case where you have a matrix with some entries revealed and you're trying to guess the missing entries. You have to make some assumptions about the underlying matrix, and low rank assumption is one of the main ones that's used. Okay. So you start with this baseline and you try and improve it. So you already bet by 4%. You need to get all the way to 10%. And the eventual winner kind of started out with this, start with the low rank approximation, and then try to kind of add additional things to correct it. Right? So they added a lot of other stuff and eventually got to 10%. Okay. All right. So this is just to give some backstory behind the low rank approximation problem, how to solve it. Not how to solve it, but why it's important. All right. And what we'll see in today and mostly in the next lecture is that so far we have two problems that we don't know how to solve. We just described them. One is the best fit subspace problem. It can be solved if you can compute the first principal components. Low rank approximation problem, and it can, it's a very important question as we just saw an example of, but we don't know how to solve it. Right? And what we'll see is that there is a magic bullet which solves both problems in one go, and this is called singular value decomposition. Okay, It's a very important theorem in linear algebra, numerical linear algebra, and in optimization. It's a lot of words, but let me state it, and then we'll look at some examples in the next lecture. So the basic theorem is an existence theorem for any matrix. If you know the eigenvalue decomposition theorem, it's a lot like that, but kind of applies more broadly. Right, so let's say I have a matrix X, which is n by d. The singular value decomposition theorem tells you that any matrix X can be written as the product of three other matrices. One is called U, which is n by R. The middle one is called sigma, which is R by R. Okay. And then you have a matrix called V transpose, which is R by D. Because the last one usually is written as V transpose. Again, this is just standard notation, so we're going to follow. So we're saying I can write X as U sigma V transpose. But what is special about these matrices and this factorization? They have many constraint properties. The first one is that the columns of U are orthonormal. Okay, meaning if I look at the columns of U as vectors, they're n-dimensional vectors. They all have length 1 and they're perpendicular to each other. Okay. This is equivalent to saying that U transpose U is actually the identity matrix. Okay. And the same thing for V. The columns of V are orthonormal. Okay, so in this representation, V transpose, the rows are all of length 1 and they are perpendicular to each other. That's why I said it's a little bit like eigenvalue decomposition. If you remember your linear algebra course, your eigenvalue decomposition tells you that I can write any matrix as any symmetric matrix as an orthonormal matrix times something times an orthonormal matrix. Right? It's a little bit like that, but here you have two different U and V. Okay. And last but not least, the matrix sigma is a diagonal matrix. It's a diagonal matrix, and the diagonal entries are non-negative. Okay, so meaning on the off diagonal entries, I have zeros, and these are all greater than or equal to 0. Okay. So the theorem says that any matrix has a factorization of this form. Can be written as U sigma V transpose, where the columns of V are orthonormal, columns of V are orthonormal, sigma is a diagonal matrix. Okay. Any questions about the statement? Yes, no? Okay, let's just do a couple of examples, and then in the next lecture, we'll connect it to the problems that we are doing. The first example I want to do is maybe the easiest one. So let's say my matrix is this. It's just a diagonal matrix. It's a 5 by 5 matrix. So what would be a singular value decomposition for this matrix? I need to write it as U sigma V transpose, right? Yeah. Exactly, right? So if I put this as X, I can put identity. And then, it's almost already in the form, right? So you have 1, 2, 3, 4, 5, and then zeros and zeros, and then I can put identity. Okay, the columns of identity are orthonormal, so this would be a singular value decomposition. Okay. Let's do another case, which is, let's say the matrix is 1, 0, 0, minus 1. Okay. So what would be, maybe let's say minus 2. So what would be singular value decomposition here? It's kind of almost in that format, but we need the diagonal entries to be non-negative, right? Yeah. No, but the diagonal has to be non-negative. So you need U sigma V transpose. Okay, so I think you're right, but basically the idea is that we want the diagonal to be positive, right? But there is a negative number here, this -2. That's the problem, right? I can sort of start out by saying, okay, I write it as identity, and then 1, 0, 0, -2. But this is not a good decomposition, not a valid decomposition, because the middle matrix has a non-negative entry, has a negative entry. So how can I get rid of it? Well, one way to get rid of it is to kind of push the negative sign over here. Okay, so whether I put -2 here or -1 here, the product is going to be the same. Again, this you can check, right? And this would be a singular value decomposition now, because the columns are perpendicular, right? They're orthonormal. Here also the columns are orthonormal, and now I have non-negative entries. Okay. All right. And this is not the only singular value decomposition. So far in the theorem, there's nothing about the decomposition being unique. Okay. It just says that there exists a decomposition. And you can check this. It's not a too complicated a matrix multiplication, but let me not do that. Okay. So this is also a valid decomposition. The columns are perpendicular to each other. The diagonal entries are non-negative, but it's not the same. Right? So we'll see that singular value decomposition is very powerful, and it can be used to solve both our problems, finding principal components and finding the best low rank approximation. And then we'll see how to find the singular value decomposition. Okay. All right, that's what we'll do in the next lecture. And remember that assignment 2 will be released today night.